Hey Sam, this is Carson, which you probably already know by looking at the who turned it in. Not sure if the other students are going to be seeing this, but anyway, I guess I'll introduce myself. This is Carson Lee, and this is my final project. And so for my final project, I decided to work on the Lorenz attractor, more specifically looking at strange attractors once inside of this model, as well as kind of the butterfly effect. So to start off, I thought I'd write a little history. Um, like I said, not sure if other students are going to be looking at this, but just in case, figure I'd explain, give a little background. Obviously, the man who discovered this was Edward Lorenz in 1963, and he's kind of the father of the chaos theory and butterfly effect. Um, and these chaotic systems have kind of been groundbreaking in the use of mathematics and physics, as we'll see later on. So the central part of the Lorenz attractor is these three differential equations and integration of these differential equations, which is a major part of the numerical analysis within my project. So within these three differential equations, we have three unique variables that kind of define each of their own equations. In the first right here, we have Prandtl's number, and here we have Raleigh's number, and then the third one we have the geometric variable right here. And I'm going to go into more detail later on when we look at the code, but these are the three variables that kind of, like I said before, make each of these differential equations unique. And these are kind of the basis for the model. So these numbers, if you change in these numbers, you'd basically be changing uh, what Lorenz worked on. So it's more about changing um, the step size. So when we look at it later on, we'll see you more have to change the surrounding variables rather than kind of these static variables that define each of the differential equations. And here I thought I'd speak on the practical application of the Lorenz attractor, since it's a pretty chaotic model and it's a more fluid in the variables. Obviously, this is used for things such as like predicting weather patterns or fluid dynamics or chemical reactions and other physical systems. Um, this, like I said before, this Lorenz attractor is kind of number one in chaos theory because it's so unpredictable. And as we'll see in the butterfly effect, none of the points that are produced are repeated. But when we have, so here I have a photo of the butterfly effect, and here we have kind of the strange attractor, kind of where all the points circle around. And this is what makes the Lorenz attractor so unique, is that this infinity symbol that is produced just from three differential equations. So we can see that there's 2 points where every point that is produced hovers around, and no matter how far out uh, and what a number is produced from differential equations, they still are kind of like sucked into the gravity of these 2 points, and the odd thing is that they never repeat themselves. So I don't know. It's just looking at it. It's I guess you can see what kind of caught my eye and made me interested in uh, working with this. So I thought I'd also go into more detail on what exactly I did. So, like I said before, the three differential equations are pretty much the lifeline of this project. Um, you don't have the Lorenz model without these three equations, as I mentioned before. Um, so that's kind of some of the numerical analysis I used, as well as the integration of these equations. Also, one of the numerical analyses I used was increasing and decreasing the step size, as well as the amount of steps, because I've figured out that if you decrease the step size, you also have to increase the steps kind of in tandem with one another. Otherwise, the resulting graph is like one line, and you don't get to see the butterfly. So that was one thing I learned working on it. Um, as well as OpenMP, that's what I decided to use for parallelism. Um, it may be more basic than pthreads or um, MPI, but I felt most confident in my OpenMP knowledge. So obviously that was the one I tend to gravitate towards. So the goal of this project was to speed up my my Lorenz code using OpenMP, um, as well as looking at the data and the what was produced, the CSV files, or I put it in a text file, but all of that data I wanted to output it into a 3D model and kind of see if I could predict or find out where the strange attractors were. And uh, the results were a bit shocking to me, but I guess we'll see later. So here's some of the tools I used on my MacBook right now. I used ECC Linux for my OpenMP analysis, and I used VS Code to write in my Python starter code, as well as um, the starter code you give us in C. As I wrote down here, this was the starter code I used, the C code that you gave us in the code file, as well as some other code I found online that I'm gonna put in my sources. But you'll see where I got that. But it's in Python. I use Python 3 to run everything and to get the matplotlib going. C OpenMP, as I stated before, obviously. And so now the code. All right. So I'll start off with my Python code. Here we have just the imports. NumPy is NP, import matplotlib, pyplot as PLT. These are kind of just boilerplate imports, but matplotlib is what I used to um, display the 3D model. Uh, I think initially I wanted to use uh, MATLAB, but it was uh, it's not very intuitive, so I wasn't really able to I wasn't really able to get it going, but I got it going here. So here we just have the steps that we're going to perform. Here we just initialize the arrays to the amount of steps that we want. Here we initialize the first variable in each array. Here we have, as I was speaking before, Prandtl's number, Raleigh's number, and the geometric factor, which always have to be 10, 28, and 2 and 2 2/3, 8/3, I think. And more about, here's the C code, but I wanted to speak a little bit more about all those numbers. So Prandtl's number is described as dimensionless quantity that plays a significant role in the study of fluid flow and heat transfer. Raleigh's number is dimensionless parameter used in the study of fluid dynamics, heat transfer, and convection. And the geometric factor is the dimensionless quantity that represents the influence of geometry or shape of an object on a particular phenomenon or property. So we can see there's a common phrase that is used to describe each of these, and it's dimensionless. So that's kind of it's Yeah, it's since it's a 3D model, it's easy to see how dimensionless is kind of the main point of each of these variables, as well as fluid flow and heat transfer, fluid dynamics, fluid flow, heat transfer, heat transfer. So we can see that kind of this chaos and unpredictability, and kind of like, I don't know, the natural infinity motion. It kind of lends itself to being used in something in physics like fluid flow or heat transfer. So anyway, back to the Python code. Those three differential equations here we can see in Python form kind of what we're working with. So here we have Prandtl's number, Rayleigh's number, geometric factor. So the first one we have Prandtl's number right here. We have Rayleigh's number right here, and we have the geometric factor right here. And these are if we wanted to compare, we can see that these mimic each other. These are identical. So obviously no switch ups here. But so we run the differential equations and we return each of their results. So that's what this function is for. We start out with a step size of 0.01. This is the step size that lines up with 10,000 steps. And like I'll show the results in just a second, but like I said before, the step size, as it decreases, the amount of steps has to increase proportionally. So if you add 1 0 to the steps, you have to add a 0 after the decimal point to the step size in order to get the picture looking all right. So in a way, we have the for loop. This is kind of where you fill up the array, and this is where we run the function from before. And we add each of these to the array, and this is going to be the data that we draw from down here, where we use plot and figure. And so the projection parameter, we make it 3D. This is just kind of boilerplate axis titles and stuff, but this is where we have the plot. So we grab all of the three arrays, and we plot it on the 3D model, so we can see the butterfly effect. And here I'll run it here. Here we go. So here we see the Lorenz attractor in all of its glory. So if we want to look at it from up top, this is kind of how it determined where it was kind of meeting. So we can see that when we start with y starting at 1, um, the it attracts more at -10 and +10 um, on the y and x axis. So 10 and 10 is an attractor, and -10 and -10 is an attractor. But we can see that the more defined kind of attractor is on the left side. And if I run out of here and I swap them and I run it again, we can see that the right side this time is the more defined attractor. So we can see that depending on which variable you initialize to 1 or more, it kind of shifts where the points are going to be more centrally located. So we can also do, I think the limit was like about 50, but say I do like 20, and again, you can see it's a lot more defined, and we also have some kind of loose data points getting out of the gravity of the attractor, but we can see it's a lot more defined in this in the 10-10 kind of meeting area. So we can determine that the more we increase the initial variable in the array, kind of the more defined it will be. But I guess I wanted to show, but if I go to like 100 and I try to show that, you see, it can't even it can't even really get along with that. It's just a straight line. So yeah, there's a couple. It's limited. The initial variables are limited, but but we have a little leeway on what we can change in the initial part. So that is the starter code for Python. And I guess I'll show they're pretty much one and the same, as you'll see, but the Python code was a lot more neat. But the C code is just the same. Here we have the steps, like in the last one. Here we initialize the variables. Here we have the step size, the integration step size. Here we have Prandtl's number, Rayleigh's number, and the geometric factor, and the initial state like we had before. But here the initial starter code only has this for loop. But speaking with you, we determined that in order to really get it going, um, we needed to add three more for loops so that we can get um, so that we can expand the data and it's not just a small little thing. But so here we have so we decided that Prandtl's number we should have a for loop that goes from -10 to +10 for Prandtl's number. And Rayleigh's number we -28 to +28. And then for the geometric factor, we decided -2 2/3 all the way to +2 2/3. And then here we have kind of here we have the differential equations from before, and here we update the current state equals the newly computed state after integration. So this is where we integrate everything, and then we kind of initialize everything back. And if I wanted to, no, I'm going to show it later. So yeah, this is the starter code kind of adjusted a little bit by me. Um, I haven't added the OpenMP yet, but so we go to my ECC Linux, and we go into my Lorenz.c. Here we have the same kind of layout as my VS Code. Um, Here I added threads and added threads and a pragma up here. I also added a pragma omp critical down here, but it wasn't really making a difference, so I just commented it out. But like I said before, everything's mostly the same. I obviously include omp.h because now I'm using OpenMP. I added the time for my clock get time. So here we have initialized variables, time spec start stop. That's for clock get time. The initialized variables from before. This is where I started the get time. This is where I have my pragma omp parallel for num threads. I initialized threads above here. Um, I didn't see a ton of change with the runtime, increasing and decreasing the threads. It more had to do with the step size. But I tested all of it and just to be sure, but I just set it at 2 initially so that just a nice number 2, obviously. Um, yeah, so like I said before, the only difference is really I added the pragma and the pragma critical from the starter code that I worked on a little bit more to get it working in OpenMP. All right, so I saved that. Make so we can see it compiles. Um, I also use time, just kind of just to be sure. And if I wanted to just prove that it was working, yeah, there, there we go. It's a lot of data. I have to delete the output file every time I run it because it's a ton of data. But I just run it. Um, we're gonna see how long it takes. Should be about 15 seconds or so. Um, it's weird. The Python code requires the 18.4 seconds. The Python code requires you to change the step size along with the steps in tandem, like I said before. But when I work with when working with the C code, it's really just the step size that kind of changes the time. So 18 seconds, and if I wanted to run, if I wanted to run it sequentially, make, we'll just see how long this takes. Probably should have deleted the output.csv file, but I think I can get like 2 or 3 runs out of it before fsync starts to fail, and then I realize I've used too much memory for data. So you can see that the OpenMP is a little bit faster. It's not as fast as I like. Um, I've been trying to get it down more. I think I got my best was getting it down maybe a couple seconds or maybe a second, but on average, it averages more. Half a second is more where we get to. But anyway, I'll just so just to do a little more testing. So if I change the step size, if I decrease the step size, we can see that it actually goes faster than than the larger step size. I don't really have an explanation for that because I was under the impression that the the larger the step size, the faster it would go. But I've come to learn that that's not the case with the C code. So that was something I learned when working on this code. We can see 16.79 seconds, and run it without the pragma. Yeah, we're gonna see that it's kind. I have a well when I show the graphs later, a little bit later, we'll see that the um, the times as the step size decreases the so does the time along with it. So that was pretty interesting discovery that I made. So we can see that see there is speed up uh, about zero point 0.3. I tend to get zero point 0.5 more often, but yeah, one last look through everything. Like I said before, the threads I had defined at two. Um, the steps, kind of the baseline was 10,000. So that's where I had it going there. Um, yeah. I guess I can prove even more that it's even faster if I make like the step size super small. One more for the road. Um, oh no, is this one gonna prove me wrong? All right, it was it was faster, although it was a lot more zeros. But it it must be more of a the curve must plateau as you can only get so small with the step sizes. I guess the time as well plateaus along with it. Um, so yeah, that was my OpenMP code. Yeah, like I said before, the starter code, my starter sequential code for my C program, and once again the starter sequential code for my Python program. So going back, what was it? The code. All right, and here I screenshotted a little more of the output. As you can see, like in the results I just showed you, um, I was getting more to the zero point 0.3 speed up, um, even though before I was getting a second, 2 seconds, or half a second speed up. Um, but I was working on a cluster before, so that may have to do with it. It might be a more optimal workspace to get the speed up that I'm looking for. Um, so here I have the results. I just went into an Excel sheet and plotted. I added 0 to the step size. Had run it sequentially and with OpenMP, and I just plotted everything, and we can see that they kind of mimic each other. Um, they both go down incrementally, and I determined it was about a 5 to 10% speed up using OpenMP. I was shooting for 50%, but this is the result I got. So that's what I have. So finally, the system info. I was running on my MacBook Pro. Total number of cores 10. Total memory 16 gigabytes. Um, yeah, that's that's pretty much it. Let me just make sure I'm not missing anything. Um, I have, um, oh, oh, it's right. Oh, I'm blind. Let me see. Yeah, I spoke on sequential, parallel design, computation, time, speed up analysis. Yes. The major goal, um, I was able to, looking at the Python, I was able to see, um, I'm able to see where the string detractors are. But no matter how much I change the variables in this butterfly effect model, strange attractors seem to converge at negative 10, and positive 10, positive 10. So I haven't, maybe there's other kind of models I need to look at, but with all the starter code I worked on and all the changes I made, all the points seem to converge on those that point. So that's kind of the result I came to. But as I showed you before, if you change the starter variables, that kind of uh, it makes it more defined. There's more central points around -10, -10 or positive 10, depending on kind of which variable you start with, whether you make x1 or y1 in my Python code. So, but we also saw that there's a limit to how high you can go with that. Um, uh, I guess I forgot to show changing the step size as well as the steps. Um, See, when we run that, when we increase the step size and decrease, or when we decrease the step size and increase the steps, we have more defined, kind of more spread out around the strange attractor. So, see, this is a big change. Let me close that. Let me just do one more, just so we can really see it. Step size down here. Once more. So now it's taking a little bit because the steps are it's a lot of steps in a small step size. But um shouldn't be too long. But I figured to be thorough, we should see the final product with this big step size. I didn't realize it would be this long, but I hope it's worth it. Hmm. I'm sure it'll pop up, but let's see. Let me make sure I got everything in here. I'm sure you're gonna. I'm sure if I missed anything, you'll let me know. We used the clock get time. Showed you my sequential files. I showed you the parallel design and the solution and the computation. So yeah, parallel speed up. This is my video. I showed you the plot with the speed up. So yeah, I think we got everything going here. All right. I wanted to show you this, but this will make it smaller. I don't know if I just did this one, but just look at it again. Yep. So from the Python code, we can see that the more steps you add, the smaller you make the step size, kind of the wider the circle around the strange attractor is. So that's kind of what I came out learning. And the hardest part from this project was probably uh, definitely the speed up. Um, I'm not sure if I implemented OpenMP incorrectly, but um, I figured I needed to add more pragmas around all the for loops or more criticals. But yeah, that was definitely the hardest part. But it was definitely a lot of fun to learn more about Lorenz attractor. I just can't stop looking at this infinity symbol, this butterfly effect. It was really interesting, and yeah, I'm really glad I did this. So thanks a lot, and have a great summer.